Hi, it's time for another math easy solution. Today we're going to go over further into vector functions and now look at derivatives and integrals of vector functions. And as always, if you don't have time to watch this whole video, you can play this video at a faster speed. Top secret life hack, your brain gets used to faster speed. You could also download and read the notes, or read the notes in article format on the Hive blockchain, and the links to that will be in the description below. And also you could watch the video in parts. Timestamps of all the parts are in the description, as well as video sections playlist. Once I'm done this video, I'll upload shorter clips of all of them. So yes, and again, everything's in the video description. Again, you can do the timestamps and skip through this intro as well. Anyways, as always, so calculus book reference. Note that I mainly follow along the following calculus book. So Calculus Early Transcendental 7th edition by James Stewart. There's links to them you can download. And I used the following solution manual for this chapter. There's a link to that. And note in some earlier videos I used the 6th edition. And again, the links are on this. You can download the notes or view in article format. Look at the description and you can find the links for that. And now what I've also been doing is adding the entire chapter and links to the notes and playlist here. So Calculus Book Chapter, the Hive notes and sections playlist for each video of this chapter are listed below. So here's vector functions, the full playlist. And there's the first video of vector functions and space curves. And this link is the link to the Hive notes, and this is the playlist. And that was the current video, derivatives and integrals of vector functions. And I'll add the link to the notes when I'm done this video, and when I make them in article format on the Hive blockchain. And now here's the playlist there, and that's already ready to go there. Anyways, and then these are the ones I'll do in later videos of this chapter. And also these links are also on MES links right here, mes.fm/links. And yeah, you can see them here. And I quickly open the website. Here's on the math tutorials, and then these are all drop downs. You can play around through it. And there's the vector functions section. There's derivatives and integrals of vector functions. And I click this, and so on. So right now it's gonna be blank because I'm just starting the series now. So once I do this video, then I'll start making clips for all of them. Anyways, so you can find everything there. So let's jump right ahead. So topics to cover. Note that the timestamps will be included in the video description for each topic listed below. So we'll go over derivatives and integrals of vector functions, derivatives of vector functions, and then go over theorem, derivative of a vector function by components, then look at example 1, derivative and unit tangent vector. Example 2, we're going to sketch the tangent vector. Example 3, tangent line to a helix. And I'll put again timestamps to all these. And now a helix surface or curve. And then second derivative of a vector function. We'll look at differentiation rules for vector functions. And then proof of formula 4, which involves the derivative of the dot product of vector functions. And then example 4, derivative of vector function is orthogonal to the vector itself. Yeah. And then go over integrals of vector functions, go over example on that. Example 5, integral of a vector function by components. And then we'll go over some exercises. So exercise 1, tangent vector points in a direction of increasing t. That's the parameter t. And then exercise 2, proof of formula 1. These are for the differentiation rules. And then derivative of addition of vector functions. Exercise 3 is proof of formulas 2 and 3. This involves derivative of a vector function multiplied by a function. And exercise 4, proof of formula 5, which is derivative of a cross product of vector functions. And exercise 5, which is proof of formula 6, derivative of a function within a vector function. All right, so pretty epic stuff. So now let's buckle up and go right ahead. So derivatives and integrals of vector functions. So later in this chapter, we are going to use vector functions to describe the motion of planets and other objects through space. Here, we prepare the way by developing the calculus of vector functions. All right, derivatives of vector functions. So the derivatives are vector prime of a vector function R, and again bold for vector, is defined in much the same way as for real valued functions. So here's the definition. All right, and this is going to be like this: d over. I changed the color. So d over dt. Yeah, this is the derivative of the R prime function. R prime vector like that. Yeah, so R with a vector on top. This equals to, well, you could write it as this, R vector prime of t. This equals to now the limit. So remember in regular derivatives definition, so limit as h approaches 0 of the difference, vector r at t plus h, so minus the vector at h. So basically, yeah, you're going to subtract that difference. You can view this as rise over run, and the run is going to be h, like that. And then as the limit as approaches 0, that is our limit. That's our derivative. And of course, this definition is only if this limit actually exists. All right, so going further, the geometric significance of this definition is shown in the figure below. So if the points P and Q have position vectors r of t and r of t plus h, then the vector PQ represents the vector r of t plus h minus r of t, which can therefore be regarded as a secant vector. And I'll draw this out. So the secant vector PQ. So basically, if we have, let's say we have, let's draw this in 3D, like this. This is the x, this is the y, and there's a z. So let's say we have a curve C, like that. This is C. All right, and now what I'll do is, let's say we have a point P right here. So this is our point P, and there's the position vector to this one. This one's r of t, like that. And yeah, so you can read it over here. So if points P and Q have position vectors r of t and r of t plus h. So now if we increase the parameter t by h, so then we're going to have here, I just quickly fix that up and put a 0 there for the origin. And now let's say we had a point all the way across here. And this is our point Q now, like that. Yeah, so we have this. And now this, from P to Q, this is our position vector, PQ. That's our secant vector. And so this one right here, this is our secant vector. And that is, well, just going to be the difference between these. And this is right here, for to write this. This is at r of t plus h. So now this one minus this, that's just a basic subtraction of vectors. So this equals to r of t plus h minus r of t, like that. All right, here I just quickly fix that up. And also note that it's called secant just because, remember the trigonometry, when you had a angle like this, this would be the adjacent, this would be the secant, like that. And there's the hypotenuse h there. And again, if this is the origin, and this would be the cross there. So the 0 there, so the secant PQ, so that's a secant vector there. All right, so going further, so if h is greater than 0, the scalar multiple 1 divided by h times by rt plus h minus rt. In other words, the secant vector. So 1 over h times this, it has the same direction as the r of t plus h minus rt. So in other words, the secant vector multiplied by a positive number, that's just a scalar multiple 1 divided by h, that is the same direction. So in other words, it's going to be the same direction like this. And as the secant vector, and remember that the 1 divided by h, that's just the terms of the limit right there. So basically, when you multiply by h, if it's 1 over h and it's positive, it doesn't change the direction, so it'd be the same one as this one here. And as h approaches 0, it appears that this vector approaches a vector that lies on the tangent line. Yeah, and essentially, basically, so if we have, this is the vector there, the terms of this limit right here. And then basically what they're saying that as h is going to 0, in other words, the difference between r of t and r of t plus h is negligible. So this cube is getting closer and closer and closer to this. And essentially it's going to be pointing along this tangent line. So if q was here, then the tangent line is going to be across like there. So basically this would be where the limit would be as you're approaching 0. So in other words, again, that is based on the definition there. So it appears to be approaching that tangent line as you move this cube closer and closer. In other words, the h goes 0. I'm going to erase these. I'm going to draw this better out as a separate table. I'm in a separate graph soon. So for this reason, the vector r prime of t is called the tangent vector to the curve defined by r at the point P, provided that r prime of t exists, or derivative, and that r prime of t is not equal to 0. So, and the derivative is not equal to 0 there. Yeah, so that's a tangent vector if the derivative exists and it's not equal to 0. And the tangent line to C at P, so basically the tangent line to the curve C, is defined to be the line through P parallel to the tangent vector r prime of t. So basically you draw a tangent line straight across the entire vector r prime of t. All right, so now let's draw this all out, make it more sense here. So part B, the tangent vector r prime of t. So again, that's just a derivative, it's just a tangent vector. So if I'm going to take this again, I'm going to copy this. Okay, I'm going to copy this and paste it here, and then we're going to play around with it just so we don't need to draw it out again. Put it right here. All right, so we put it there. And what I'm going to do now is I'm going to erase this. So that's just our secant vector there. And now what I'll do is I'm going to draw across here. This is going to be our the secant vector multiplied. So this right here is going to be the terms of the limit. So r of t plus h minus r of t divided by h. So it's the same direction as a secant vector, like that. And now this part right here is going to be, well, the tangent line. This is going to be if h is approaching 0. As h goes to 0, this would be the tangent line on this line right here. That's the tangent vector r prime of t. So, or in other words, the derivative. All right, and now going further, we can show this by an animation I just illustrated also. Here is a secant / tangent line animation someone made with GeoGebra. And also before we get to that, so again, the tangent line to C at P would be a line that's parallel to this tangent line. So it'd be across like this. This would be the tangent line all the way across this and parallel to, I mean, it's going to be parallel. I was going to draw it, you have to draw it straight through it. It's going to be parallel straight to that. So that'll be the tangent line. So I'll just erase that. And I drew that just so that you don't get confused with, you don't get confused with this r of t. So these ones are typically, not necessarily parallel. So this one is going like this, and it goes to the right there. Anyways, so that's that. And I'm going to go here. Whoops, actually I meant to go here. So here's the GeoGebra. So someone made this animation, and I'll read the name out. So this is by Mukta Badari. Okay, apologies if I pronounced it wrong. So here is an animation. So this is the point P, but they have Q on the opposite side. I'm just going to move this over. I'll move P here just so it matches ours. And I'm going to pause this. I don't want to play I don't want to play the animation actually. I'll pause this. Okay, and now we can scroll up. Okay, so there it is. And zoom in. And this is our point P, point Q. And what I'll also do is go up here. So we have the A there. We can, so basically this is part of the equation there anyways. So you could, if you move this, so notice the secant vector. Here's the secant vector, and there's the parallel vector. That's terms of the limit will be straight across. That just be, so basically parallel to this one. And then as you get closer to P, it's following along this tangent line. So there's the red is the tangent line of the tangent line on the curve and this one is like a semicircle. So and then if I just go like this, it's getting closer to it, and it lines up with it. So there it is. When it's on it, it goes like that. Then going opposite, and it's always tangent. It's tangent at the point there. So at the point, it's perfectly tangent with the curve. Everywhere else is just a secant line. Notice it's extending out, and so on. And you can also move this further manually. Oh, you can't do it manually. Okay, I think they locked it up. Okay, so anyways, so that's how it looks like, and that's just the curve there. So that's just to illustrate it. As you get closer to this one, as Q gets closer to P, in other words, the H value approaches 0, then they basically coincide. So as the points P and Q are closer together, the secant and tangent lines become the same, i.e. the derivative is the instantaneous rate of change, i.e. rise over run of the curve. So in this case, there's the rise. So the difference between these two curves of the value divided by the parameter difference H there. So this one is R of t plus H minus R of t divided by this. So very similar to regular real valued derivatives. All right, and lastly, we also have occasion to consider the unit tangent vector, and that is just basically just defined as, this is as capital T of, capital T vector of, with the, based on, or of T of the small parameter T equals to, and then this is just the derivative of the vector function like that, or of the tangent vector divided by the distance of it. So it's the unit tangent vector basically divided by the length of it, so that you have a length of 1, but then all it is just the direction of the tangent vector. So that is just, it's going to be useful later on. All right, now let's move forward and look at this theorem now. This is derivative of a vector function by components. So the following theorem gives us a convenient method for computing the derivative of a vector function R, just differentiate each component of R. So basically to find a derivative of this vector function R, just to take, basically differentiate each component. Yeah, so pretty straightforward. So theorem, if R, a vector function of t, is equal to and the components are f of t, so these are just regular functions, so inside as a vector. So f of t, g of t, h of t, and now this equals to, again, just using the ijk format, sort of like that. So f of t I plus g of t j plus, I'll fix these thingies like that. And then, g of t j, and then h of t k. And where f, g, and h are differentiable functions, so they all have derivatives, then the derivative, so r prime of t is equal to, well, this is the derivative of each component, and f prime of t, g prime of t, h prime of t. Again, in 3D, this would be the x, y, and z component of this vector function. And then, again, in ijk format, you can just write it like that. So ijk, those are the unit vectors in the x, y, z direction. Yeah, so f prime of t, I, g prime of t, j, h prime of t, k. So let's take a look at the proof of this, and we're going to use the definition of the derivative for a vector function. We're going to use this right here. So let's take a look at that. So I'm going to go, and because we have an h there, so instead of writing h, I'm going to write delta t in our definition. So this is going to be the vector function like this, r of t prime is equal to the limit, as we'll use delta t, so the change in delta t, in other words h, but because we have an h there already, so we'll just change the variable. So 1 over delta t, or h, this is going to be now, this is going to be r of t plus h, plus delta t, minus, this is a secant vector, and this is going to be a vector. It's going to be a vector, and then this is going to be minus r of t, like that. So just put it like that. Just want to multiply this in. All right, now we could expand this by using the components, because again, these are all just, they have f, g, and f, g, and h functions within. So this is the same thing as writing or just expanding it out. So limit as delta t approaches 0 of, and what we'll do now is, I'm going to put, this is be 1 divided by delta t as well. And then we're going to have a big bracket like this. And now this is going to be, write it as, just expand that function out. This is going to be, as a function, as a vector, this is going to be f of t plus delta t. And then g of t plus delta t. Yeah, so that's this part right here. This is this whole function there, and then this is going to be h of t plus delta t, and this is like that. Yeah, and then this is going to be a minus now, minus. Now this part here now. So now we do that this one over here. So that's going to be f of t, and then this is a bracket. I forgot to put it. This is going to be the triangle bracket for a vector, and then subtracted by vector phi of t minus. Not minus. Now it's g of t, h of t, like that. Okay, so we got that. And here what I quickly did was pause the video and then just put it all as one line. So I just moved it and shrunk it. So this is going to be this right here, and then this is going to be this right here. Yeah, so that's those are the two parts. And now keep going further. This equals 2. Yeah, and then what we can do is I'm going to put all of these delta t's inside here. So we're going to have a whole bunch of these. But also what we could do is, so we can multiply that, but also before that, we're going to also subtract these all. So we can just take these two vectors and subtract the components. So this f of t plus delta t, then we're going to subtract by some minus f of t, and then multiply this in here, so we're going to divide by delta t. So this equals to limit as delta t approaches 0 of, and now we're going to have a, this is a giant bracket. I'm going to go like this. And now this is going to, the first one is going to be, well, f of t plus delta t. I mean, this is f of t inside of that. It's t plus delta t minus f of t divided by delta t, like that. And then the next one is going to be the same thing for g of t plus delta t, and then minus by g of t, and then divided by delta t, and then same for h. So we'll do this all now. So it's going to be g of t plus delta t, plus delta t minus g of t divided by delta t. And this is going to be, next one is h of t plus delta t, and then minus h of t divided by, divide this all by delta t, and then close bracket like that. All right, and here I quickly just shrunk that in to fit in as well. And now the next one, now we can put the limit in each one. So again, these are just basic limit laws for vectors, as I covered in my earlier videos. You just put those inside. These are just the components. So now we're going to have a giant vector where we have a limit as delta t approaches 0 of, now this whole part there. And I don't want to write this all again, so I'm just going to copy this and then paste it right here. So that's just one right there. Now the next one is going to be, again, limit as delta t approaches 0. And now we, again, do it for the same for this one. Copy this and move this over right here. All right, now the next one is going to be limit as delta t approaches 0, and copy this setup there, like that. And this is just going to be close. Oh, whoops. Yeah, whoops, I accidentally moved instead of copied. So I just paused it and moved it over there. So just fix that up. And now, yeah, and here I quickly paused it again and shrunk that to fit in. So now this just equals to, well, this just equals to, this is just the derivative of, just regular definition of derivative of a function. So that just equals to, well, now components, we're going to have f prime of t, g prime of t, h prime of t. So there it is. We just proved it. Because these ones are all just the derivatives of just normal functions. So there it is. And I'm going to box this out and do a check mark. So there's our theorem. So if these r of t is equal to, it has components f, g of h functions, differentiable functions, then the derivative is just equal to the derivatives of the components. And there it is. All right, and now let's take a look at an example going over all this. So basically, derivative and unit tangent vector example on that. So part A says find the derivative of r of t equals to 1 plus t3 I, the unit vector, plus t times e to the power of negative tj plus sine of 2tk. Then part B says find the unit tangent vector at the point where t is equal to 0. So let's take a look at the solution to A. So according to the earlier theorem, we can differentiate each component of r. So again, we just take the components. So the derivative here equals the derivative of the components. And so let's just write that out. So let's write out the whole thing first. So we have r of t, this equals to 1 plus t3, this is going to be our I unit vector, and then plus t e to the negative tj plus sine of 2tk. So then the derivative is going to be, well, r prime of t. This equals to, well, derivative of the component. So this one here, derivative of 1 is just going to be 0. Derivative of t3 is going to be, just remember our derivative law, put the 3 down and then subtract by 1. So 3 times t to the power of 2. And this is going to be our I. And now this is going to be, yeah, the next one here we're going to use, well, this is going to be product rule. So the derivative of t times by, e minus e to the power of negative t. This is going to be negative t, like that. So first we need to take the derivative of t. So derivative of t is just going to be equal to, well, 1. It's just a constant. So that's 1 multiplied by e to the negative t. And then we have to take the derivative of e to the negative t. So we have to do now t times it by derivative of e to the negative t. That's just going to be, well, derivative of e of the exponential function is itself. Then using chain rule, multiply by derivative of negative t, which is negative 1. So this becomes a negative 1, like that. And then this is going to be j, like this. Now the derivative of sine of 2t, that just equals to, well, cosine of 2t, and then derivative of 2t is just going to be 2. So put the 2 in front, cosine 2t k vector. And we can simplify this even further. So this just equals to, well, 3. This one's already simplified. 3t squared I. Now this one here, we could factor out the e to the negative t. So we're going to have a 1 minus t multiplied by e to the negative t, like that. Yeah, so just simplify that. Then j, just because the calculus book does that, so I'll just do that as well. This is going to be now plus 2 cosine 2t and then k, like this. And yeah, I'll just box this out like that. So there is our derivative. All right, and now let's take a look at the solution to b, and that's right here. So basically, find the unit tangent vector at the point where t equals 0. So, and recall the unit tangent vector, that's just here, right here. So the unit tangent vector is equal to the tangent vector divided by the length of the tangent vector. In other words, yeah, just the derivative divided by the length of that derivative, so that basically we make it into just the length of 1, because you're dividing by it. So basically, now we're gonna just solve it. But before we get to that, and it's also at the point t equals 0. So let's just solve for the unit tangent vector here, r prime of t at 0. So right here, let's put it like this: r prime of 0. This equals to this is going to be, well, plug these inside. So 3t0, yeah, 3 where times by 0, that's just equals to 0i. Now plus, right here, bracket 1 minus t0, then e to the power of negative 0 is just 0, like that, j. And now this one right here is by definition equals to 1. Typically, that's definitions being used. Now this is now 2 cosine 0, so the t, 2t0, k vector, and then again recall on this one here. This is equal to 0. So I'll put a this equals 0, and again you can recall quickly if you have a trigonomic function. Just recall quickly. This is the theta, and I'll do this like this. This is going to be let's say this is cosine theta. So this is the graph of this is the graph of cosine. So add 0 equals to 1. And these are just lengths 1. This is negative 1 here. This is 1 there. Yeah, so that's just cosine. Yeah, so then what this equals to, well, this equals to 0i. That's just 0. And then we can just ignore it. Now this one right here, 1 times by 1, that's just going to be, 1. So we'll just put a j. And then 2 times 1 is just 2. So plus 2k vector. This is j, and there's the k. So that is our unit, that's our vector. Our tangent vector at t equals 0. And also note, let's just take the regular value. So note that r of 0, just so we know what the point on is. Well, my calculus book does that. So let's go to the normal one right here. So all 1 plus t cubed. So put a 0 there. That just becomes 1. So we're just going to have a 1 plus 0i. Now put a 0 in here. T is 0, so that just vanishes. So it's going to be plus 0 j. And now this one here is sine 2t and 2 0, so that's just going to be sine. Move it down here. Plus sine 0, that's going to be sine 0, and then this is k. And I'm going to draw this in red. Just recall that sine 0, that's just going to be like this. So this is going to be our sine. And 0, sine theta, and then add 0 is equals 0 as well. So we can go write our black, and I'll just cross this out. So this equals to 0. So this just equals to, well, I. Yeah, so this just equals to I. Yeah, in other words, this equals to I, which equals to, well, again, that's just a unit vector at the x component. Everything else is vanishing. So this, in this format, the triangle bracket equals to 1, 0, 0. All right, so thus the unit tangent vector at the point 1, 0, 0. And notice this is a point, this is a vector. Again, this is a position vector. It points to this point. So anyways, so at the point 1, 0, 0 on that curve, the unit tangent vector is, and then let's just write this out now so we know our values, or at least the unit tangent, at least the tangent vector. So this is at 0. This equals to r prime of 0 divided by the length r prime of 0, like that. This equals to the top part we already know, that's just j plus 2k. Yeah, so let's write that out. So j plus 2k, and these are vectors. And now divided by, now the length right here, remember the length is just going to be the square root of each component squared. Again, that's just a distance formula in 3D or 2D. I'll show that, I'll recall that formula soon. But basically, this is going to be our, so the x one is going to be 0. So 0 squared plus, now this is the j, that's going to be, well, 1 squared. Plus, now this one is going to be, the k there. And the 2 there, that's going to be the z component, so 2 squared. Like that. So that equals to, this is going to be equal to, well, before we even do that, this is pretty straightforward. So this is going to be 1 squared is 1 plus 2 squared is 4. So that's 5. So this equals to square root of 5. So then we just multiply that inside. So we'll just have a 1 over square root 5 of j plus 2 over square root 5 of k. So there it is. Yeah, here I just moved it over and let's just box this in. So there is our answer. All right, and now recall the distance formula that I used over here. So recall distance formula in 3D and 2D, just make the z component 0. And basically the distance formula is linked to my earlier video. And basically distance between P1, P2, this is, you just write it like this, P1, P2, and then those are the points there. Difference between those points is equal to square root of, and then the squares of the difference of all the components, so x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared, and all square root. All right, so now that we have that, let's go over example 2. And this one states, this is on the sketching the tangent vector. So for the curve listed below, find the derivative r prime of r vector prime of t and sketch the position vector r of 1 and the tangent vector r prime at 1 at t equals to 1 there. So there's the function right here. So if the vector function r of t is equal to square root t times I plus 2 minus t times j, so the j vector, unit vector. All right, so let's take a look at the solution. So we have, so let's first get the derivative. So r prime of t, this equals to, this equals to, well, this is, now we take the derivative of square root t, and recall the square root t, that's just equals to 10 to the, t to the 1/2. So we would bring the 1/2 down. So we would bring the 1/2 down and then subtract it by 1. So 1 over 2 minus 1, so in other words 2 over 2. That becomes negative 1 over 2. So that's just going to be equals to t negative 1 over 2, I, like this. And now this one here, the derivative, this is equals to, well, 2, 0. And then this one's negative, derivative of t is, negative t is negative 1. So we have just negative j, like that. So in other words, this equals to 1 over 2, and then square root, let's put a square root at the bottom, so I'll put this like this. 1 over square root t, like that. This is going to be I minus j. All right, and let's box this in like that. And now we could just solve for, so we need to sketch the position vector r1 and the tangent vector r prime 1. So let's just plug those in to see what the values are first. Yeah, so what we get is, well, r, put an arrow like this, r prime of 1, this equals 2, we'll plug that t inside. So 1 over 2 times square root of 1, that's just 1, so it's just 1 over 2. Yes, this becomes 1 over 2. I vector minus j vector, like that. So that is this one here. So now we have the derivative, and we have derivative at 1. And then lastly, let's get the point at just a regular vector there. So r1, this equals 2. Let's plug these values. So that's going to be square root of t. So basically square root 1i plus 2 minus 1 j. So this equals to, well, I, and this is going to be plus j. Like that. So there it is. All right, now let's go further. So the curve r vector t is a plane curve, and elimination of the parameter from the corresponding parametric equations gives. And what I mean by the plane curve is because, well, there's no z component here. So basically, the z components can be all infinite values. For example, if this is just a random line like this, but then if it's in 3D, you have to account for all of the z values of it, which are infinite. So you're basically going to get a surface like this. Something like that. Anyways, so we need to sketch this out. So we're going to sketch it. So let's get rid of the parameter t, because these are just parametric equations inside. And then basically we'll have a function in terms of y and x only. So let's write this down. So we have r of t. Let's just write the whole thing out. This is going to be square root t I plus 2 minus tj, like this. That's this one right here, 2 minus tj, like that. So now this equals to, now basically the parametric equations are, this is just saying, well, we have x is equal to square root t. So basically write these out as parametric equations. Y component is going to be equal to 2 minus t. So in other words, if this is t like that, so I'm going to square both sides. So I will square this. I'll just square this. I'll just square this. Square this, we end up with, well, x squared is equal to t. So in other words, t is equal to x squared. Throw that inside, we get y equals to 2 minus x squared. Yeah, so there it is. So y is equal to 2 minus x squared, which is the parabola. Or I'll just put this together. So then we get y is equal to 2 minus x squared. So we have a parabola, and it's going to be a surface because you have all values of z. All right, so and now we're asked to solve for, again, sketch the position vector r of t and the tangent vector. So r prime of t. So let's draw these out. So in the figure below, we draw the position vector r of t, r of 1 equals to I plus j. That's just this right here, starting at the origin, and then the tangent vector r prime of 1 starting at the corresponding points 1, 1. That's they're basically starting at this point right there. Yes, in other words, position vector, we start from 0, the origin, to it at 1, 1, and then the tangent vector is at tangent at 1, no, at this 1, 1 point. So we draw the vector from there. So let's draw this out. So and we also know that the curve is this y equals 2 minus x squared. So if we graph this out as just the x and y axis. Okay, there's the x, there's the y, like that. So now, so what I'll do is, so now it's going to be the curve 2 minus x squared. So in other words, it's going to be an inverted parabola. So we have the 2. It starts off, when you plug in x0, we get y is 2. So it starts off here. So there's our 2 value. And then it goes all the way down. And for example, you could say that well, actually, we don't need to do that because it's a minus x squared. So we're going to be minusing. So in other words, it's going to be an inverted parabola like this. And we're only going to look at the positive x value there. And this value should be, actually, if you plug in y0, y0. So we'll have this 2 on the other side. So square root 2. That's just square root 2 there. So we have this. And now the next point is draw the position vector. R of 1 is just at 1, 1. So that's going to be at 1. Let's say we have 1. This is going to be at the halfway point. 1, 1. Let's say it's over here. And here I quickly fix it up to make it more of a parabola, less of a like a spherical shape. But anyways, so this is the point 1. So point 1, 1 should be across here. Yeah, so this is at point 1, 1. This is at 1, 1. So this is the point 1, 1, like that. So this is the vector from here to here. This is the r of t vector, like this. 1, like that. And now the position vector, the tangent vector, we're going to start from here. I'm going to draw this in red. And that is going to be, well, let's look at this. It's going to be 1/2 I and then minus 1. So that means we go to the right 1/2. So if this is 1/2 would be somewhere around here. So let's say if 1 is over here. So let's make it, and then so it goes halfway here, and then it goes down by 1. This right here. So this is positive to the x-axis, half of 1.5, then minus 1. So 1 on the y-axis. So it goes down 1. So it's going to be across here. Yeah, but this is at the halfway point here. So here all the way to 1. So it's going to be something like this. It's a bit off. But anyways, that is how it should be. Yeah, so like that. This is actually a bit more circle. It's actually closer here. So yeah, so that's the red one there. So yeah, it looks pretty legit there. So there is our vector. I'll draw the arrow. It's going to be, again, there's the directions like that. And this is going to be, this is markers for just for my own sake. This is going to be at r prime of 1. Like that. All right, and going further, notice from the above figure that the tangent vector right here, this r prime of 1, points in the direction of increasing t, and that's because well, we know this equation of this this curve is y equals 2 minus x squared, where x squared is just t. So as you increase x is going down, so it's increasing t is going downwards, and this is in the direction of it. And it turns out it's always in the direction of it, and that's basically C exercise 1 at the end of this video. It's very interesting on that. Yeah, and basically this tangent vector is always in the direction of increasing t. So, and also to illustrate this, and also that the regular curve right here in 3D is a plane curve, as I mentioned right here. So r of t is a plane curve. I'll graph it out in GeoGebra to see how that is. So here's how the plane curve looks like in 3D using GeoGebra's 3D graphing calculator. And also I also added a vector right here, so you could also play around with the tangent vector there. Now note what I did was, well, here's the plane. So if we have y equals 2 minus x squared, but if you draw them in 3D, that means the z value is going to be infinite. So you basically draw your parabola, and then you draw it for the entire up and down. And hence that's why it's a plane curve like that. And here I also drew the curve right here, and I used a instead of t, and the reason is when you use a, you could use it as a variable. You can't use t as a variable for some reason in GeoGebra, so I just used a. So this is just the curve a, square root a, or a to the power of 1/2. That's just this part right here, then plus 2 minus t, or 2 minus a. And then that graphs it out, so you can graph it out at the bottom like that. And furthermore, what I did, this vector right here, you could use the vector equation. So this is the beginning point, begin, and this is the end point. And the way I did this is basically I inputted, this would be the input of the curve. So this is the exact same equation right here. This a1, a to the power 1/2, that's right here. 2 minus a, 2 minus a. And then 0 for the z component, just because it's just flat there. And then the second part here is the end point. Well, the end point, I wanted basically the, it's basically at the tip of the vector right here. So this endpoint, well, what I have to do is I have to add this r vector plus the r prime vectors, and that's what we have here. So basically I have this is a1/2, and then plus 1 divided by 2, then square root a, or that's this part right here. This is the r prime vector. So I just added, no, this one right here. And then minus 1, so there. So then, so basically, and then I would go 2 minus a, and then minus 1. So I'm adding those as the ending vector, and then basically you can get that there. But anyways, I'll click that, and let's go and see how this looks like. I think I have it opened already, right here. So I have it opened right here, and there is the curve. It's pretty epic stuff. And you could see that. And now this one right here, you can move it, and it's always, as you change the value of a or t in this case, or t or a in this case, you can see it's always tangent to it. And there it is, and then it becomes basically, because it's parabola, it flattens out like that. So what I'll do is, I'm going to go like this, all the way across here. Yeah, so you can see that there's a bit nicer there, and then you can also play around with plane curve. there's a surface on there. There's a surface. There's a plane. And yeah. So yeah, epic stuff there. All right, let's get back here. All right, and continuing further, so example 3, the tangent line to a helix. So in this example, we're asked find parametric equations for the tangent line to the helix with parametric equations x equals to 2 cosine t, y equals sine t, and z equals to t at the point 0, 1, and pi over 2. Alright, so we want a tangent line, so we basically have to take a derivative, but first of all, the vector equation of the helix is, well, we just put this in vector form, suppose that as a vector, so this is going to equal to, I'm going to write this as r vector of t, this equals 2, put the components all together to 2 cosine t, sine t, and then t. And then when we take a derivative, so we get the tangent vector, r, like this, r prime of t, this equals 2. Well, this is going to be cosine t, the derivative is negative sine t. So this equals to negative, then put the 2 there, sine t. Then this one, derivative of sine t is just cosine t. And then derivative of t is just 1, like that. All right, and now the parameter value corresponding to the point right here. So it's at this point, so we want to know what value of t to get that point, 0, 1, pi over 2. This is just going to be equal to, t equals to pi over 2. So the tangent vector is, well, before that, the calculus book doesn't solve it right away, but I'll do it myself. So note, let's just do it for completeness. So note that r of t, r vector at basically, the vector function at t equals to pi over 2. Well, this equals 2. So 2 is 2 cosine t. So we basically put that all inside. So this is going to be 2 cosine pi over 2. And we know that cosine pi over 2, that's just 0, as we showed earlier. Over here, there's over here. So cosine pi over 2 is going to be, this is going to be right here. This is pi over 2. So that's going to be 0. So we have 0 there. All right. So that's going to be equal to 0. So this equals to 0. And then the next one is going to be, this is sine t. Oh, sine pi over 2. And that just equals to, well, 1. This equals to 1. And then lastly, t is just pi over 2. So that's just pi over 2. So we've solved this all. And I put them like that just so it lines up with it. And again, sine pi over 2 is just 0 as per here. So sine, it's equal to 1. Sine pi over 2 is right here. This one would go, here, let's just fix that up actually. It should be at 1. So this goes up all the way there. And this one is at 0. And then this goes at minimum when that's 0. Whoops. And then it goes to 0 when, this goes 0 when that goes max. Yeah, so that is the one value right there. All right. All right, so thus, so we have this, the tangent vector, and we have this point, so now we can just find the tangent vector at that point. So thus, because we want a tangent line to it, so thus, r prime at pi over 2, or t equals to pi over 2, that's just equals to minus 2 sine t, minus 2 sine pi over 2, and that's going to be 1. And this is cosine t, cosine pi over 2, and then lastly 1. So then this is going to equal 2, well, this equals to, well, 2 sine pi over 2, that's just 1, so that's going to be negative 2. And then lastly, this one here is going to be 0, cosine pi over 2 is 0, as we just illustrated here. This is 0, this one is 1, and then lastly 1. So negative 2, 0, and 1, like that. All right, so going further, so now the tangent line is the line through the point 0, 1, pi over 2 and parallel to the vector negative 2, 0, and 1. And again, we're asked to find the parametric equations right here of the tangent line at this point of this helix parametric equations curve. All right, so by my earlier video, and I put a screenshot of that here, the parametric equations can be obtained, and basically recall the parametric equations of a line. So if you have the vector equation of a line like this, r equals r naught plus r vector, plus t times, so you have plus a parameter t multiplied by a tangent vector like that. is t plus v. But now in our case, we have the point 0 there, and we have a tangent 1, and we have the parameter there, so we get solve for the whole setup there. And then this equals to x, y, z over here. And then this, you can split them up into their components. So the r naught vector, x naught, y naught, z naught plus, and then parameter t times abc, where abc is just the, is this one right here. ABC is just a tangent vector there. Or the parallel vector, I mean. And then add them all up, you get x naught plus ta, and then y naught equals plus tb, z naught plus tc, and then you can separate them in terms of their x, y, and z component, and you get it like this. All right, so that is what we have. So in our case, or actually write it down. Right, in our case, yeah, so in our case, what we have is, well, the x naught, y naught, z naught, so the starting point right here, the p naught, is going to be, yeah, this one right here, x naught, like that. I'll just put it like this for completeness. Actually, I'll just ignore that. So yeah, this is equals to now, at our starting point is just going to be this point, 0, 1, pi over 2. So this equals to 0, 1, pi over 2. And then the next one is, well, we have a parameter t, and then but then this point ABC, that's just the parallel vector. So this is the v right here, and then parallel to yeah, basically it's parallel to this one here. And then you add those up there and multiply by parameter. So we get a b c equals to, well, the tangent vector. So parallel vector is going to be tangent vector. In this case, it's going to be negative 2, 0, 1. Negative 2, 0, 1. So what this means is, well, our parametric equations are x equals to, well, we just add these up, x naught plus a. This equals to 0. Yeah, so 0, I mean, x minus a, then t. There's a t there. So we have 0 minus, yeah, minus 2t. And then the y1 is going to equal to, that's going to equal to y naught. I'll erase this. Y naught plus then b, and then bt. This equals 2. Well, y naught is 1, is right here, and then this is the 0, and then plus 0t. Again, this equals to, get rid of that other one there, so negative 2t. This one's equal to, well, 1. So we're going to just actually circle these. I'm going to box these in. Yeah, because those are actually part of our answer for our parametric equations of the tangent line. So now the z1 is going to equal to, well, z naught plus ct. This equals to z naught is pi over 2 plus the c times, yeah, is 1 times t. So this t. Yeah, and that is what we have here. Yeah, and for completeness, I'll just write it down a summary right here. So thus the parametric equations of the tangent line to the helix are, so we just have x is equal to negative 2t, y is equal to 1, and z is equal to pi over 2 plus t. Like that, so that's what we have. All right, and now if we basically see how the helix looks like, well, this is from my calculus book, and I'll graph it out in GeoGebra soon. So the helix and tangent line are shown in the figure below. So here it is for a screenshot from my calculus book right here. Yeah, so you can see the helix going like that, and there is the tangent line like that. So here's the same graph using the GeoGebra 3D graphing calculator, including the tangent vector across the entire helix, which I just added that part, which is quite fascinating. So first of all, here's the helix. You could just write curve and write basically the parametric equations: 2 cosine t, sine t, and t. And then from t is between 0 and 10 pi, and so on, and just so it can cycle up and down. And going further, and then the tangent right here, you could do a tangent line equals to, just put the parametric equations, negative t1 and then pi over 2 plus t. So t is a special variable in it, so you can't just replace it with a. So what I had to do is something else. So, but anyways, so that's the red line. So the red line is here. Here's the tangent line. There's the helix in the black. And then to get the vector, basically I did the same thing as before. I would set the variable a, and then I would have the vector from the beginning point, beginning, and then end, and then the next one is ending. So that's the beginning. This is from here to here, And then the next one is ending point, and I would have to add. So the beginning, I would just put in the Helix equation, parametric equations, but it replaced t with a. So 2 cosine a, sine a. That's just this part here. And then the next one is I put the same one, but then I add the derivative, add the tangent vector. So the tangent vector going back up here, the general one is right here. So negative 2 sine t, cosine t, and then 1. So replace that with a instead of t. And we get this right here. Yeah, so we get, I'll zoom in. Yeah, so we get over here, this is going to be, yeah, so 2 cosine t, and then minus 2 sine t, but then replace with a. And now the next one is sine, and then plus the cosine. And again, you could just take the derivative sine t, cosine t, replace with a. And then the next one's going to be t, or a, plus 1. And 1 is just derivative of t. So yeah, so then, and then basically that'll be the end point. So that's the end. Then when you subtract it, you get this vector, and that graphs out exactly as it is. So let's go to it. All right. So there it is. If we click this, I have it opened already. So there it is. And there is the helix, like this. There's the equations, and so on. Just hide this here. And now what you can do is you can adjust this, and you can see how it is. So you can adjust it. And then at t equals pi over 2, that's going to be about like 1 point, because pi is 3.14, so about 1 point, what is it? 1.57, I think, yeah, I think 1.57, let's do that quickly. Pi over 2, so pi over 2 is equal to, it should be 1.57 equals, I don't know why it's not doing it. Equals pi over 2 equals to 1.57. So if we go to around 1.57, it should line up pretty much almost in sync. There's 1.5, so there's the tangent line in red, and there's the tangent vector, and again, it's almost exactly it. And it goes up and up and up and up. There's tangent to it. So again, fascinating stuff. And again, you can play around with it. Oh, the link, you have the link that's right here. It'll also be in the notes and so on in PDF and article format on the Hive blockchain. All right, and now let's go further and now look at the second derivative of a vector function. So just as for real valued functions, the second derivative of a vector function, you have a vector function r is the derivative r prime, that is r double prime is just equal to, well, the derivative of r prime, so we're going to have a double prime there. So basically we just take the derivative again and again, just repeat the same thing. So for instance, the second derivative of the function in example 3 is, and if we recall the derivative of example 3, that's this right here. So r prime of t is equal to negative 2 sine t cosine t, and then 1. So we have, just recall, this is going to be equal to, this is of t, equal to negative, this is going to be sine, yeah, negative 2 sine t, and then this is going to be, yeah, cosine t, and then we'll just take it with, and then 1, like that. And I quickly teleported here, just double check. So negative 2 sine t, cosine t, and 1. Yeah, so that's what we have. And then the second derivative, well, we just take the derivative of the derivative. So this equals to r double prime of the vector function, and derivative of negative 2 sine t. The derivative of sine is just cosine, so we're just going to get 2 cosine t. Then this one here, derivative of cosine t, that's going to be negative sine t. And then derivative of 1 is just 0. So that's what we have. Yeah, so we could just box this whole thing in. And now note that in a future video, we will see how the r prime of t and r double prime of t can be interpreted as the velocity and acceleration vectors of a particle moving through space with position vector r of t at time t. Yeah, so stay tuned for those videos. And now go to the next section, so differentiation rules. The next theorem shows that the differentiation rules for real valued functions have their counterparts for vector valued functions. So here's a theorem. Suppose u and v are differentiable vector functions. C is a scalar and f is a real valued function. Then, and I'm going to list them all here, and I'll also show a screenshot of my calculus book just for more concise typing there. So we're going to go, the first property or a differentiation rule is just regular addition or subtraction. So d over dt is the derivative of the addition of two vector functions, u of t plus v of t. This just equals 2, well, you could just separate these. So we could just take u prime plus v prime. So that's the first one, and I'll prove all these in exercises. And then theorem or property 4 or rule 4, I'll do that like right after this one. So number 2 is going to be, well, this is just going to be if you have d over tt, and if you have a constant, so if you have a c, u vector like this, t, and then the derivative of this is just gonna be the same thing as taking the c out and just taking the derivative of the u. So just take the constant, c is a scalar or a constant. Just get that out of there. So now the part 3, this is gonna be differentiation part 3, or property 3. So this is d over dt equals to, I know that now we have a function. So instead of just one, these ones are pretty much the same thing. This one's just a constant or scalar. This is the function like this, and then u of t. This equals 2, and then this one would just have to use product rule. So this will equal to f prime of t, u of t, like this, and then plus f of t, u prime of t. Okay, like that. So we have that. And now the next one is number 4. So number 4 is going to be d over dt, and this one is the dot product actually. So this is going to be, now if we have a u of t dot v of t, this equals 2. Yeah, this equals 2. Well, it's actually going to be very similar to this above one, just using product rule. This equals to u prime of t, and then dot v prime of, just v regular t, and then plus, now we do the reverse. So u vector dot product with the v vector prime of t. So it's kind of like the product rule, but with dot products. So fascinating stuff there. And now the next one is going to be this part 5. This one's going to be using the cross product. So d over dt, and it's going to be the same thing as the dot product one. And then that'll be cross v vector of t. This equals 2. This is going to be u prime of t cross v normal, and then plus, and now we do the other side there. This is going to be u vector t cross v vector prime of t, like that. And now the last formula or rule is going to be number 6. This one involves the chain rule. So d over dt of, you have now u vector, instead of t, now we have a function is inside as a parameter instead of just a regular t. So that equals to, now then basically what this equals to is, well, using chain rule, well, we're gonna have to what ends up happening is take the derivative afterwards. So we're gonna have this f prime of t gets out of there, and then multiplied by, well, u prime of t. So the order would be, you take the derivative u prime of t like this, and then take the derivative of the inside function f of t and take it out. So again, this is just chain rule. Chain rule. Put this in normal bracket. Yeah, just put that chain there, and then rule like this, like that. All right. All right, and going further, so we have these rules, and now here's a screenshot of the list from my calculus book, just to make it more concise. So there it is, and also that was a way to double check there. So this is how it looks like. So yes, and basically there's those 6 there. And now this theorem can be proved either directly or by the definition of a vector function derivative, or from the theorem on differentiating vector functions by components. And I'll be doing that. I'll be using both to prove them in the exercises. But I will prove the formula 4 right now. So the proof of formula 4, that's the dot product derivative. follows. The remaining formulas are left as exercises at the end of this video. So proof of formula for derivative of dot product of vector functions. All right, and basically if you have the dot product of two vector functions, the derivative is equal to, well, just using basic product rule, but with dot product there. You have a normal product rule for that. So what we'll do now is, so let's expand the dot product and write as a summation. But first I'm going to let u of t equals 2. And what I'll do right here, I'm going to write this as f1. So the components are f1 of t, and then f2 of t, and then f3 of t, like that, for the z component. And now let v of t is equal to, now that's f, so let's use g now. So g1 of t, g2 of t, and then g3 of t, like that. All right, so then the dot product of this, so then recall the dot product. Well, this is just going to be, I'll write that and then write then u, like that, u of t dot v of t. This just equals 2. And if you recall, basically dot product, you just multiply this by this, so each component and add them up. So you multiply by their corresponding components and add them up. So we're going to have a f1 of t times it by g1 of t plus f2 of t, g2 of t, like that. And then we'll have a plus f3 of t, and then g3 of t, like that. This is like that, t, like that. And now what I'll do now is my calculus book solves it. It writes this as a summation. So this equals to the summation from I equals to 1 up to 3. And then we'll have fi of t, gi of t, like that. All right, so basically what we've done is taken the dot product and then write it as a summation. So now the ordinary product rule gives, and we'll just write this out. And that's because we're going to be taking derivative of these two. So these are two normal functions, but that's using a summation. So instead of just doing it on one term, but they're doing it multiple times. So it's still the basic ordinary product rule, but for just multiple terms added up. So let's take the derivative now of this. Again, the product rule. This is equals to the dot product of the beginning one. So u vector dot product with v vector. So we know what these equal to. So this equals to, in terms of the summation, which is a normal product rule, not a dot product. So this is going to be the d over dt is equal to the derivative of the summation from I equals to 1 up to 3 of f of I t, and then g of I of t, like that. And now this equals to, well, this is the same thing as just writing just the summation. Let's write it here. This equals to put it inside the summation, because it doesn't matter, because you're going to just do it separately. So it's 3. It's just using basic summation rules. And now this equals to d over dt of, and now the inside product there, f of I t, and then g of I, g sub I of t, like that. And now the derivative of these, this one for each single one, we just apply the product rule. So this is going to be f sub 1 prime of t times by g of t, g1 of t, and then plus f1 of t times g prime of t, and do it for each one. So in other words, we're going to get a summation of the product rule of derivatives. So this is I equals to 1. This is going to equal 2 now. We just take the derivative using product rule. Fi prime t gi t, like that. And then plus, now the reverse way. The reverse way is basically f prime of t, and then times by g prime of t. So derivative of the f times normal g times, and then plus the normal f times derivative of g. So that's what we have, and now we have a addition. We have an addition in the summation. So we just separate these into two summations. So this equals 2. This is I equals to 1, And now we have a, I'll put this in a, yeah, we just write it like this, fi prime of t, g prime of t, plus summation, I'll write this a bit better, 3I equals 1, f1 of t, and then g prime like that, of t like that. So that's what we have there. And well, what does this equal? This just equals to the dot product this is the dot product of the terms that have f. In other words, that's dot product with u prime. Because remember here, so remember here, this part here, the dot product. Yeah, this dot product equals to this. So, but now if we're having the prime there, this means we have to do the prime. Yeah. So then, in other words, these are equal to, yeah, so this equals to, it's just a dot product with the u vector prime. And then the other one is just v prime t normal. Plus, now this one is going to be, well, u vector like that of t. Yeah, we're just going backwards now. And now this is just going to be, and this is a dot product. Yeah, for the dot product there. So dot product, this is going to be dot product. Yeah, here I just fixed that up a bit, made it a bit more separated to see the dot product. And now the next one is u prime of t dot v prime t. Yeah, so these primes, these are all just the the v primes there. And that is just the dot product there. And this is basically, we just solved theorem 4. All right, yeah, so that's theorem 4, and we just box this in. Yeah, so that's fascinating stuff there. And yeah, I'll just do a check mark there. And again, we have the dot product here becomes the summation, and now we just have a prime there. So now we go reverse, but we have a prime in each one, and the prime just becomes over there. So there's the dot product for theorem 4 like that. So u dot v becomes like a product rule. So derivative times normal, and then dot product, the other one, and then normal dot product, the derivative. So fascinating stuff. All right, and now let's go further and look at example 4. And this one will show basically the derivative of a vector function is orthogonal to the vector of constant length. And basically, we'll run down what this all means. So we're asked to show that if the length or the distance or the absolute value of the vector function r of t is equal to constant. So if it's equal to a constant c, then the derivative, or the vector, or the tangent vector, r prime of t is orthogonal to r of t for all t. So basically, if this is constant, then the derivative is going to be orthogonal or perpendicular to it for all values of t. So let's take a look at the solution. So first, recall the geometric interpretation of the dot product. Yeah, so here is the dot product right here. So we have a dot b is equal to the absolute value or the length of a times by length of b times by cosine theta. And then if cosine theta is 90 degrees or pi over 2, this would go to 0. Yeah, so then this would equal to 0 at, this is at equals to 90 degrees. Or pi over 2 radians. So then that basically means that we'll have a perpendicular setup. So 90 degrees like that. So that's if the two vectors a and b are perpendicular. So if it's perpendicular, it's going to be equal to 0. So keep that in mind. All right, so let's consider the dot product of the vector function r of t with itself and apply formula 4 of the vector function's differentiation rules. And basically the formula 4 is the one we just solved for the dot product. So basically when you have the dot product right here, the derivative of them, you could just take it as you would with a regular regular product rule. So we just take derivative dot product with the function and then do the other way around. So when you have two different functions like that. So let's go ahead and see what happens. So we're going to take dot product by itself and apply formula 4. Okay, so first let's take the dot product by itself. So if we have r prime of t, dot product by itself, this equals 2. And we're going to use this geometric interpretation. This equals 2. This is just going to be absolute value of r. Like that. And then again, it's going to be absolute value of r. So we just put a square there. Or for completeness, I'll also include it as well. So we're going to have it times it by like this and put the t there. R r vector of t like that, and then cosine theta. And in this case, well, cosine theta, that's just going to be 0, because if this vector right here, if we have, this is basically parallel, yeah, and this equals to 1, and again, this is because we have a parallel vector. Vectors, and here, quickly fix that up. I just put a theta equals 0, that just basically means we have parallel vectors. And because a vector by itself, and then, yeah, so if you have vector r, well, r of t, the other vector is also r of t, so it's basically the same thing. So basically r of t is going to be in line with it as well. So these are both r of t, so it's again the same thing. It's just on top of each other. So that is parallel vectors there. This is pretty, I'll just move this over like this. Yeah, and we'll just put a bubble like that. All right, so that is that. So then what this ends up happening as well, and we know cosine 0 is just 1, so this just becomes, this is just squared. So this is just r of t like this, squared. And furthermore, well, we're given that if this is equal to c, so it's a constant, so then the squares is going to equal to, well, c squared. So we have this r of t dot product of itself is equal to c squared. And yeah, so thus by formula 4 we have, so let's just take the formula 4 as just the derivative of the dot product. So d over dt of r vector like that, dot product r of t vector. This equals 2, and then we just expand that out again. We just take the derivative. I'll just do it for completeness sake. So derivative right here, dot product with the normal one, and then the plus the normal vector dot product with the other one there. So this is going to be equal to, just for completeness, this is going to equal to r prime of t dot, yeah, it's going to be dot product with r of t plus r vector dot product r prime of t like that. So that is that. And these are the same thing, we could just add these up. Yeah, so before we get to that, well, we know the derivative of this, our dot product by itself is equal to c squared. Yeah, it's equal to d over dt. And then this is going to be just, again, this is r of t dot product with itself is going to be c squared. Like that. And then derivative of a constant is just 0. Yeah, so and then we could also, now we have this derivative right here, dot product. And now we could just, well, these ones, we just add these up. This is just going to equal to, and again, because it doesn't matter the order of it for dot product, r prime of t dot r of t is the same thing as r of t dot product r prime of t. So then we can just add them up, and I just put this one in front, doesn't matter which one we choose. So r 2 times r prime of t dot product with r of t, like that. And we can divide by 2 to both sides, just cancel it out, just get rid of it. And basically what it means is, well, we have now, so thus, I'll put this like this, thus, r prime of t dot product with r of t is equal to 0, and it also equals 2 by the geometric interpretation using the absolute value signs like that, and then cosine theta. So this equals to the length of r prime of t, then multiplied by the regular length of the regular vector function, now cosine theta. And now for this to be 0, well, it's either these ones are zeros, but again, we're not dealing with trivial values of the vectors. This one has to be 0, so equals 0. So in other words, thus we get, so thus we get cosine theta is equal to, well, cosine pi over 2 equals to 0. Yeah, so or multiples of that and so on. And we get theta equals to pi over 2 radians. I'll just put red for completeness. Equals 90 degrees. And yeah, 90 degrees, which equals to, well, again, this is orthogonal like that. I'll just put a better one like this. So it's 90 degrees. In other words, we get, this is just orthogonal. Orthogonal. Let's put an exclamation mark like that. And I'll just circle this. So basically that angle, yeah, so that's how we get cosine 0. And then, yeah, so it's orthogonal. And yeah, so thus r prime of t is orthogonal to r of t when it's constant. And I'll put this when this is equals to a constant, just so that it's not always the case, just for this case. And then this is when, I'll paste this in here, when the distance r prime of t, I mean just a regular r function, r of t, a vector function equals to c, a constant. Yeah, and going further, so geometrically, this result says that if a curve lies on a sphere with center the origin, then the tangent vector r prime of t is always perpendicular to the position vector r of t. So for example, if we had a sphere, I'm just going to draw this like this. So we had a, this is the z, this is the y, this is the x component, and let's say we had a giant sphere around this, like that. So that's our sphere. Let's draw like a dashed line around like that. And let's say we had, yeah, just make it, just give it some 3D depth. So let's say this is a sphere. Let's draw this a bit, one time better again. Let's draw an actual sphere like that. And let's say we had a shape like this. I'll make it like this, okay? Yeah, last one. Okay, so and now we have the r vector is over here, but it's a sphere, so it's always the same. So r prime of t, so it's always the same, doesn't matter where you go, this is always the same. So the distance right here equals the constant, so it's always the distance c. So the distance is always c, doesn't matter where you go. So then basically you have a giant sphere, and then basically the vector of it, the tangent vector is always perpendicular, so this is perpendicular. And that is what we would expect. So there it is. So tangent vector is always perpendicular to any point on the sphere when this is the constant distance there. All right, and now to better illustrate this instead of just this drawing. So I've made a sphere in GeoGebra using Grok AI to obtain the parametric equations of the sphere and the tangent vectors, one in the vertical rotation and one in the horizontal rotation. Yeah, so when I used it, it just gave me two tangent vectors. And here's a link to the GeoGebra, and the link to the Grok AI is over here as well. And yeah, so I just use that to quickly get the formulas and so on. It's a bit out, because it is a bit out of the scope of this video. But anyways, so what happens is this is how it looks like. Here's a screenshot of it. This parameter a, that's actually just think of that as just theta. I just didn't want to use the theta or the phi symbols. This is going to be the horizontal rotation, and this one is the phi. This one is the vertical rotation, or vertical angle, like that. And then there's the radius r, and you can play around with that. And there's the sphere, so there's the parametric equations of a sphere like this. And yeah, so it gets these parametric equations like that. It makes a sphere like that, and there's a point here. This point is just a point on it. Basically, this is the full sphere. This is a point on the sphere. So if you have a sphere like this would be a point P on it. This one here. And then there's vector A. This is actually a tangent vector, but this one is as a point. So tangent vector A, this would be on the horizontal rotation. So it should be somewhere like this. This would be the vector, and I'll show you how it is soon. So vector VA. This one here is this part right here, vector B. That's in the horizontal, vertical rotation. It's going to be something like this. So it's just going to be VB. And then I basically had a position vector, but this one's just a point. And then the position vector is going to be from the origin. I have it all the way to P like that. So vector, and then as a P. And then here's tangent vector, and basically tangent vector A. I go from the point P here to the point vector A. So then we basically get this. It draws an actual arrow. And this one is tangent vector B there. And it actually makes it. And it looks like this. So there's the two vectors, and they're both, these are perpendicular. Now assume these one are as well. Because it's, yeah, vertical and horizontal. So this one is on the horizontal angle, like that. That's the B angle. And this one is the A angle. Actually, this one is the A angle. This one's A slash phi. This one is B slash, yeah, I mean, this is theta. This is phi. This is phi. This is theta. Yeah, so that's either or. Yeah, the Grok initially gave it theta and phi, but I just switched it to A and B. So anyways, there's a tangent vector. There's the position vector straight across there. And you could see it right here, and let me just go straight into here. So let me just rotate. Oh, okay. So yeah, refresh it. All right. So here is the equation. So I took the screenshots using my computer, and I made it with my computer, but then my laptop here is much slower. So anyways, I'll just shift this over here. So it is slower, and it's having trouble graphing out the full sphere. But when you click the link, if you have a fast computer, it should show up. Let's move this over like this. And it should show up the full sphere, but it takes a while. So notice how it's still getting all the calculations. But anyways, so what happens is, here's what I mean by the rotation. So if I rotate this one's a vertical rotation, the B, and then there's the horizontal rotation. So guys, there's a horizontal rotation. There's the vectors on it. Notice it's always perpendicular. So again, it's always perpendicular to it, and you could adjust this to 10. I can see it go to 10. Yeah, it keeps going on and on. And there is the radius. You can make it smaller and bigger. Doesn't matter where you make it. It's always going to be perpendicular to them. So notice how it is. It's perpendicular to it. So again, pretty pretty epic stuff there. So I had to make it, and so on. And then going, here's a point P. There's a point P is right here. So there's the point P. You can see this one here starts disappearing. And there's the sphere, and then there's the vector. Yeah, vector is just a point there. It says vector B, but it's actually just a point A and B, where the tangent vector leads to. And then you have to actually write it as a vector, position vector. Here's position vectors inside, and so on. And then lastly, this was the, I think there was a surface there somewhere. Yeah, actually, never mind. That was an old formula that initially showed up on Grok. But anyways, so here's the final one, and it's again looks pretty absolutely amazing stuff there. Yeah. So again, play around with it, and there's a link there, and so on. And yeah. All right. Let's continue further, and now look at integrals of vector functions. So the definite integral of a continuous vector function r of t can be defined in much of the same way as for real valued functions, except that the integral is a vector. But then we can express the integral of r, the vector function, in terms of the integrals of its components, component functions f, g, and h as follows, and using the notation of my earlier video, and basically this is my earlier video on on integrals / areas under the curve. So basically, and I just want to bring this up because the notation is these are the sample points, is this part right here. So if we had a curve like this, and then basically the whole idea of integrals is you just find the area under it, so you would have geometric shape. So here's just a rectangle like this, but it's using the height of this rectangle is going to be this sample point x1 between a and x1, right there, or x naught there. This is x naught or 1. So this is the point there. But the whole idea of this x1 star, it doesn't need to be the endpoint. It doesn't need to be x1. It doesn't need to be x2. So if it was x2, it would go like this. If it was x1, it would go like this. But it's just any point in between them, because there's some different methods. You could do the trapezoid rule or midpoint rule, etc., for trying to get better accuracy and better efficiency on these areas. So so what you'll have is this one is over there. This sample point is anywhere in between. This was on the right side. Notice, and then you would draw the rectangle across it. And that's basically the notation we'll use. All right. So for vector functions, what we'll have is again the same setup. So integral from a to b of this is going to be the r vector of t, like this, and dt. This equals to the limit as n approaches infinity. And now we would just sum these up. So we're going to go summation up to n, and then this is I equals to 1. Yeah, so we're just going to sum up a bunch of rectangles, and be r vector like this, and then the value for the height of it is going to be at the parameter ti star. So it could be anywhere in between t1 and t2. Doesn't need to be t1 or t2. And then delta t like this. And again, from here, this could be as you can view this as delta x, and this height right here is fxi, and in our case, it's going to be r ti star there. Yeah, this xi star there. And again, you just sum all these up, you get the area under the curve, and that would be the integral, as you get an infinite number of these. So in other words, you shrink this delta t to infinitely small, and then you get the integral. And then and since we have components, and typically they're 3-dimensional, what we'll do is I'll just move it over here, equals to, for our setup, this is limit as n approaches infinity. As n approaches infinity, and this is going to be, now we're going to do all the components, the I, j, k. So we're going to go summation n, this is I equals 1, and now we'll have the f. So yeah, so this is the x component right here. All right, f of, and then this is going to be ti star, and then delta t, And then this would be like a big bracket there. And then I star is the I component. Now we do the next one is going to be the same thing. I equals 1. This is going to be G is the Y component. And then put the star better there. Delta T. Oh, whoops. Delta T. And then this is J star. And then keep going. The next one's so I mean F G H. So the next one's would be H like that. I equals to 1, and then H of T. I star like this, and then delta T, and then this is going to be K. This is the K or the Z parameter. I mean the Z unit vector. So close this out. Now what I'll do is, and yeah, what I'll do is what I just did was just pause the video and just shrunk it so it fits all in one line. And now, so now that we have these are all just, again, you can put the limit inside every single one of these components. So those are all just going to be the integrals. So for each component, this is integral of, again, it's going to be the same thing right here. When you sum this up, area is going to be area under the curve as you take the limit approaches to infinity. Yeah, as the number of rectangles goes to infinity, you basically get the integral. So thus, the integral of a to b of r vector like that, t dt equals 2, and this dt is again just delta t but infinitely small. This equals 2, and then we're going to take, this is going to be integral of just the regular function f, integral from a to b of f of t dt, and then definite integral just from a to b, that's just what it means. And this is going to be I, and then plus integral from a to b of g of t dt, and then this is j. Now the next one is going to be, again, same thing, integral from a to b of h of t, h of t dt, like that, and this is k, like that. Alright, here and I just quickly pause the video, shrunk it again, and we're going to box this whole thing out like this. So this is the integral of vector function. Basically, integral of vector function is just integral of its components. And yeah, this means now we can evaluate an integral of a vector function by integrating each component function. We can extend the fundamental theorem of calculus to continuous vector functions as follows. Yeah, so if it's continuous, there's no breaks in between. So we could extend it out into just this setup like this. Integral from a to b of the vector function r of t dt, this equals to, well, this equals to capital R of t, where this is the antiderivative, in other words, the integral. This is going to be capital R of t as a vector from a to b. And again, what this equals to, just solve it. Integral from integral of b like that. This is a definite integral definition. So recall that from my other videos again, and then subtracted by R of a. So, and this is the antiderivative. And yeah, here I just wrote it down. So where capital R is an antiderivative of R, that is R prime. The derivative of capital R is equal to the lowercase r. So yeah, basically, yeah, the antiderivative. So going backwards. So the derivative of this one is equal to the vector function r. So, and we use the notation, this integral sign r of t dt for indefinite integrals or antiderivatives. That's when we're not evaluating it from a to b. Just in general, just get what the actual antiderivative is. And we'll go over an example on this. So example 5. Integral of a vector function by component. So if we have r of t, the vector function, is equal to 2 cosine t I plus sine of t j, write this a bit better, and then plus 2 tk, then, well, the integral is going to be, so the integral is, so then integral of r, or the antiderivative, r of t dt is equal to, well, the integral of the antiderivative of cosine, that's just sine. So this is going to be sine of t, because derivative of sine of t is just going to be cosine And now the integral of sine of t, or the antiderivative, that's negative cosine t, because the derivative of cosine is negative sine t, but then so you have to cancel out the negative, so include another negative. So negative cosine t, because again, derivative of cosine t is negative sine t. So we need to cancel that out. J, and then the this one here. So this one here, t, well, 2t, so the derivative of t squared is 2t. So this is going to be t squared, k, like that. But lastly, again, when we deal with this indefinite integrals, we need to include a constant. In this case, it's a vector, so a constant vector of integration, because the derivative of the constant is going to be 0. So basically when we take a derivative, because this whole thing's an antiderivative, so when we take a derivative, we get a 0. So in other words, this is 0 there. So whatever this value of this constant is, it will always be 0. So we need to account for that this could be anything there. And so I wrote that down. So where capital C as a vector is a vector constant of integration, again, because any value that will still fit this antiderivative, or will match this derivative of it, or will become an antiderivative of this right here. So and also, and now we'll just do a quick example on doing a definite integral on that. So the integral from 0 to pi over 2 of r of t dt. Well, this just equals to, let's write this better, r, like that. This equals to, well, now we just evaluate this whole thing. So we already know the antiderivative, which is 2 sine ti minus cosine tj, and then plus t squared k. And now we're going to evaluate it, and then we can ignore the c, because when we subtract them, that just cancels out. So now this is going to be from 0 to pi over 2. So we could plug these inside. So we're going to get a setup like this. We'll have a 2 sine pi over 2 minus 2 sine 0. Like that. Let's put it all for completeness. And then minus, this one's going to be a cosine pi over 2 minus cosine 0. And this is going to be j. And I'll move this over, this whole thing. Move it over here. All right, so we moved it over there. And then lastly, this is plus, and then this is going to be a t squared is going to be, well, pi over, pi over 2 squared minus 0. 0 squared is 0, so do that. I'll put another bracket. This is going to be our k. It's good. I just put it for completeness. Now let's just start solving all these. Well, again, recall sine pi over 2, that just goes to 1. So this is 1. And then sine 0 is 0. And this one right here, cosine pi over 2 is 0. It's always, and then cosine 0 is 1. And this one is just pi squared over 4. So this equals to, 2i. And now this next one's going to be minus, this one's a 0, then minus 1, minus negative 1, that's going to be plus 1. So plus j. And then lastly, the last one is going to be right here, pi over 2 squared, that's just equal to, well, plus pi squared, just put that inside, and then pi squared over 4. Okay, yeah, so that is what we get. And we can just box this whole thing in. Yeah, so that is just the definite integral from 0 to pi over 2 of this vector function over here. And here is the indefinite integral, or the antiderivative, and here is the definite one when you're evaluating from 0 to pi over 2. Alright, and now we pretty much covered the chapter, and or the section of this chapter, and now look at the exercises. So exercise 1, tangent vector points in the direction or in direction of increasing t, or the parameter t. So we're asked here, show that the tangent vector to a curve defined by a vector function r of t points in the direction of increasing t. All right, so and here's a hint. Refer to the earlier figure also shown below and consider the cases h is greater than 0 and h is less than 0 separately. So consider this cases and basically look at this right here, either less than or greater than 0, and then see what happens to this direction. So this is the this is the derivative right here, and this is the secant. Secant vector as a tangent vector, and as this approaches 0, this becomes the same, and basically saying is t if t is increasing here, this would be in the direction of it. If t is increasing on the other side, it would be this would actually be the vector function. I mean the derivative of the vector function, and that's what it's saying. So we have to prove that, and let's see what happens. So solution. So the tangent vector r prime of t is defined as, so basically this, but the limit as h approaches as 0 there. So we get let's recall the definition. So this is what it's defined as. Again, just for recap, this is equal to limit as h approaches 0 of, now we go r of t plus h minus r of t. So the difference, so the rise, think of it as rise over run, but this is like 3D with parameters. Now this is going to be h like that. All right, and now here we assume that this limit, this limit exists, and that the derivative r prime of t is not equal to 0. So let's say it exists and it's not equal to 0, and then we know that this vector lies on the tangent line to the curve. So basically, this is the tangent line straight across there. So we know it's going to be somewhere like this, up or down. And so on. So it's going to be in one of those directions. Yeah, so as in the above figure, let points P and Q have position vectors r of t and r of t plus h, and the vector r of t plus h minus r of t points from P to Q. So then the difference right here, r of t plus h minus r of t, is equal to just a PQ vector, or the secant vector. And now I'll draw this all out. So if h is greater than 0, then t plus h is greater than t. So q lies ahead of p. So ahead of p in there. All right, so let's draw this out. So I'm going to draw it like this. This is the I'll draw it like this. This is the y. This is the z. Okay, that's the z, and now this is the x component. Like that, and now this is, we're going to take the case, look at the case for h is greater than 0, like that. So h is greater than 0. So let's say we have a curve like this. Again, I'm just going to draw this one out again, but just draw it out, and we're going to draw over it. So let's say it's like this. Okay, it's something like that. So this is the point P. So this is point P is going to go at r of t. All right, here I just quickly fix that up, just make it like that. And this is a point P. And let's say we have a point Q right here. And I'm going to just extend this out. Yeah, here I just quickly extend it out. And then say this is our point Q like this. Yeah, so now this one right here, this is r of t plus h. So if this is greater than, if this is greater than t, that is, in other words, h is greater than 0. Yeah, so it's greater than 0, so then this has to be bigger than it. So if it's on this side, this would be ahead of it. So basically t is increasing along this side, so t is increasing, increasing, like that. All right, here I just quickly fix that up. So increasing t is on this side where q is quote ahead of p on the curve. Yeah, and this one's ahead, and then basically this difference right here, this r of t plus h minus r of t, that's just going to be this vector. Whoops, this is just going to be this is just going to be PQ. Yeah, so this is PQ. Like that vector. And this is ahead of it. And again, this is just R of t plus h like that. So that's just that one. And again, yeah, you could recall that how you can add vectors. So R of t plus PQ equals to this one. So then to get this one, you just move this over to the other side. And then you subtract them. And right here, if h is sufficiently small, we can take h to be as small as we like, since h approaches 0 in the limit. Then this PQ vector or secant vector approximates the curve from P to Q. So as you shrink h right here, so this t plus h, it basically gets smaller and smaller until it pretty much coincides with this P and Q. They both basically coincide together, and hence points approximately in the direction of the curve as t increases. Basically what it means is as you shrink this q right here, as you basically make the h approach 0, it gets closer and closer to this, and then basically the p and q pretty much coincide, and what we get is, well, we get the limit right here, r prime of t, and it's going in the direction of increasing t. And going further, so since h is positive, 1 divided by h times pq, the secant vector, is just going to equal to, well, just a positive number or scalar multiplied by this right here, r of t plus h minus r of t, r of t divided by h. So it doesn't change the direction. It's the same direction. You're just going to multiply by that. And points in the same direction. So in other words, this is pointing in this direction there, and this right here is going to be pointing across. It's going to be parallel to the PQ, so it doesn't change anything. So this is going to be 1/2. I'll put it fully like this. This is just going to be r of t plus h minus r of t divided by h. So again, this is in the direction of the increasing t, and then as you shrink it, as you get q closer to p, in other words, h approach 0. This becomes in line with this. That's the tangent line. This is the secant line, which is the same direction as this, like that, because you're just multiplying by 1 over h, just a scalar, not changing anything. We're only changing the length. We're not changing the actual, direction, like that. All right. And going further, so if h is less than 0, then what we're going to have is t is greater than t plus h, so q lies behind p on the curve. So here's, I just took the exact same one, I just copied it and pasted it here. So now let's take a look at the case where h is less than 0. So if we have h less than 0, so again, what this means now is instead of having a scenario like this, we actually need to go backwards. So let's pick our point P right here. So that's our point P. This from here to here is going to be our r of t. And now this is going to be our new q, just to illustrate it, instead of dealing with the exact same points. So now this from here to here, this is going to be r of t plus h, like that. And now this part right here, again, this right here is less than, because h is negative, it's less than 0. So this is going to be less than t. So this is going to be, I'll just put a less than t. So t is greater than this one. So in other words, this is going to be, this is basically behind p. But in this case, if this is t there, if this is less than this one, so we still have an increasing t here. So we still have increasing t like this. And here I quickly just pause video and just copy and paste this increasing t. So we're still graphing it such that we're increasing the curve, the t from this side over there. But now this q is on this side, so then this PQ is going to be coming across this side like that. So that's our PQ. And now we'll just read out what I wrote here. Again, it's from the solutions manual. So for h sufficiently small, PQ approximates the curve but points in the direction of decreasing t. So this is pointing now decreasing t. So if increasing is on this side, so now this is going towards decreasing. However, h is negative. It's because h is negative. So 1 divided by h times it by PQ is going to be, well, this is a negative number. I mean, this is pointing, if this is pointing in the direction going negative, but now you're multiplying by a negative, so it's going to be this this vector r of t plus h minus r of t divided by h points in the opposite direction because of the negative sign. That is in the direction of increasing t. So in both cases, the difference quotient r of t plus h minus r of t points in the direction of increasing t. So in other words, this right here, and I will draw this right here, it's not going to be pointing this way. So now notice this one is pointing this way, but then now we're going to have a pointing this way, like that. This is going to be over here. This will be our. I'll draw this. Where could we write it here? Yeah, I'm just going to say that's going to be opposite of that. That's going to be. I'm just going to write this as 1 over h, PQ, like that, and which is the same thing as the Again, it's the same thing as this one, but now the h is negative. So it's going to be pointing opposite of this. And I will draw, again, this is parallel to it, parallel to this one. But it's in the opposite direction. And going further, right here, in both cases, difference quotient points in direction of increasing t. So it's pointing in this direction of increasing t. And then the tangent vector r prime of t is the limit of this difference quotient, so it must also be point in the direction of increasing t. So then this is going to be basically once you get it exactly. Yeah, well, I mean, since this is q, this is approaching here. So once as h approaches 0, this q is going to be moving to the right. So we're actually going to have a tangent. It's actually going to be like this. I'll erase this thing here. Let's say the curve is like this. So then the tangent's going to be actually like this. So it's in the direction. So this is going to be our r prime of t. And this is in the direction of increasing t. So there it is. So regardless, it's always going to be increasing t, regardless if h is a negative or positive. Hence, we proved this setup here. So show that the tangent vector to a curve defined by a vector function r of t points in the direction of increasing t. So the direction vector, the tangent vector is always pointing in the direction of increasing t. So if you want to know which way a function or which way is the t increasing, you can either graph it yourself or just take the derivative at any point, and you'll know where it's going there. All right, and now let's continue further and look at exercise 2, and this one looks at the proof of Formula 1, which is a derivative of addition of vector functions. So we're asked proof Formula 1 of the differential rules for vector functions. Actually, I just fixed that up. I meant differentiation rules for vector functions. And this is the Formula 1, which is d over dt of u of t plus v of t equals to u prime of t plus v prime of t. Basically, the derivative of two vector functions when you add them is equal to, well, just each individually take the derivative of them. So let's take a look at the solution. So so let u of t, so this first vector function equals to, just have comprised of these three functions as components. So u1 of t, u2 of t, u3 of t, and then the second vector function v of t has components v1 of t, v2 of t, of v3 of t. So these are just real valued functions as components, and this is a full vector function. So taking the derivative of the components, we obtain, so let's take a look at the components. So we go d over dt of, and I'm going to write u of t plus v of t equals, yeah, so this just equals to, well, this is the same thing as writing d of dt. So now we're going to add these components. So we're going to add the components and then and put them as one function like that. So it's going to be u1 of t plus v1 of t. And now the next one is going to be u2 of t plus v2 of t. And then we'll get the last one is u3. So we're just gonna add the components u3 of t plus v3 of t, like that. All right, and now we I just shrunk it and put it in one line. So now this fits over there. So what I'll do now is I'm gonna put an equal sign here. So now we can just take the derivative of each one. So we'll just put this d over dt inside each one. So we're gonna get a d over dt of instead of writing it all, maybe I could copy this. Yeah, copy and paste. And here I just quickly pasted it there, and then move it here. So we copied and pasted there, and then put this bracket like that. All right. And instead of doing it always, I'm just going to go like this. Just saves time. So copy that. So again, we just put those together. Now the next one is going to be d over dt like this. And then change these to u1, u2. And this is, u2, v2, like that. And then same thing. Paste this again, move it over here. And yeah, box this up. This is going to be 3. So again, just to save time there. Yeah, you get the idea there. So now we put the derivative inside each one, and now we just take the derivatives. This just equals 2. Now this is going to be, well, u1 prime of t because now these are just real functions. These aren't vector functions anymore, and we could just use the basic properties of functions. When you take the derivative, when you add them, is the same thing as yeah, this is 1, this is a prime there. Okay, this is a prime. Because these are real value function, and we already know that the derivative, you could just add them up like that. And then this is going to be u2 prime of t plus v2 prime of t. And that's pretty much how we're going to solve all these properties of vector functions, derivatives. We take derivatives and then basically of components and make them, and then just follow the real valued function rule, derivative rules, and they're pretty much the same thing. And we get the same thing for both, so or the same corresponding one. So u3 prime plus v3 prime t, like that. And just like right here when we added these together, now that we have all these, so we added these together. Now we could just well, separate them now. So instead of writing these together, we'll just this is the same thing as writing two vectors separately. So this is going to be u1 prime of t, and then u2 prime of t, and then u3 prime of t, plus, and now we get a v1 prime of t, v2 prime of t, and then v3 prime of t. In other words, we get two vectors combined, and then we can just write them as two vectors combined. So we can just write this as u prime of t plus v. This is, we don't need to put a, this is a vector now. Never mind. Yeah, this is the vector that has components as functions. Yeah, like that. So we get rid of that one there, and this is going to be now prime. We have v prime of t. So we could box this in. All right, and yeah, that's pretty basically what we got there. So I'll just put a check mark there, and again, it's exactly this right here. The derivative of two vector functions, when you add them, it equals to the derivative of them separately, and then add them. All right, so let's continue further, and now let's look at exercise 3, and this one involves the proof of formula 2 and 3, and basically involves the derivative of a vector function multiplied by a function. All right, so, and basically it states right here, so prove formula 2 and 3 of the differentiation rules for vector functions. So this is formula 2, d over dt of c, which is a constant, times it by the vector function u of t. This equals 2, basically just the same thing as writing the constant multiplied by the derivative of the vector function u. And then the formula 3 is more general. This is just the same thing as formula 3. Formula 2 is just a special case where the function is a constant c. So here's formula 3, d over dt of f of t times it by the vector function u of t. This equals to the derivative, just using product rule now, derivative of f, so yeah, f prime of t, times it by the vector function u of t, plus the f of t function times it by the derivative now of the u prime of t. So let's take a look at the solution. So solution, note that formula 2 is just formula 3 for the case f of t is equal to c, where c is a constant. Yeah, so basically we'll show that it's formula 3, so then all we need to do is prove formula 3, and that auto proves formula 2. So d over dt of f of t, like this, yeah, this is going to be just formula 3. This equals to, well, this is the derivative of f prime of t. Well, in our case, we're going to be taking the derivative of d over dt of the constant c, and then times it by, this is just going to be now, I'll put this like this. This is separate, and then times it by u of t, like that, plus, now just the function f of t, which is just c, times it by, yeah, now we just multiply it by u of prime of t, like that. And now this right here, derivative of a constant, just equals to 0. So then basically what we end up getting is just c times it by u prime of t. So basically this is formula 2. So that's formula 2 right here. It's based on formula 3. So now we just need to prove formula 3, and we've proven everything there's to prove. All right, so let's go further, and now let's prove formula 3. So let u of t equals to, again, as per usual, equals to the components u1 of t, u2 of t, and u3 of t. So now taking the derivative of the components we obtain, so let's do this. So d over dt of f of t and then this is going to be u vector function of t, like this. Take the components now. So this is the same thing as writing d over dt of its components. So put this in vector format. It's going to be just f of t, and it's multiplied by each component. So u just real valued function. So u1 of t. So not the actual vector function. That's just the now we're taking each component. So this is f of t, ut of t, and then lastly, this is going to be f of t, u3 of t, like that. And here I quickly just paused and shrunk it as per usual to fit it all in one line. So now the next part as well, we just put this d over dt inside each of these components there. So we could just use that. Again, just basic vectors. Now we put that inside the d over dt. So we're doing a derivative of each one. And this is going to be now f of t, u of t, and then d over dt. And now this is going to be f of t, u2 of t, and then d over dt, f of t, u3 of t, like that. All right, here I just quickly shifted it over, and now we could just take the derivative of each part right here and using just basic product rule. So this would equal to this part right here will just be f of t. Again, just basic product rule for real valued functions. F of t, and then u of t, u1 of t, and then plus f of this f prime of t, u1 of t, and now this is regular f of t, and then u1 prime of t, like that. Now the next setup is it's gonna be now f of t for the middle one, and I mean f prime of t, and then u of t, like u2 of t. And then we have to add up again. This is going to be f of t, and then u prime of 2, u prime of 2 t, or u2 prime of t. Yeah. All right. Now the next one's going to be f prime of t, and then u3 of t, and then plus. Now we're going to do plus. Move it over. This is going to be f of t, u3, this is prime of t, like that. Yeah, so that is what we have there. All right, and here I just quickly just paused and then shrunk it in to fit this line as per usual. Okay, there is what we have. And now what we'll do is, we could just take the like terms or just separate these into two vectors, and then basically getting all the all the derivative parts in here at the f1, the f primes. So get all the f primes out of there, and then the other one separately as well. So this is going to equal 2, and also what we're going to do is factor out, I'm going to factor out the like terms. In this case, is the f prime. So the derivative of f. So this is going to factor that out. F of t, this is going to be now it's going to be, and then put as a bracket, u1 of t, and then we have u2 of t, and then u3 of t. And now we do plus, and now we factor out the other parts. So just, I'll keep that in like that. I'll do this now. I'll keep it like this. So now we'll just do this part now. So we, again, now this is going to be a closed bracket. Now we add a second vector, and then like terms is just regular function f of t. And then times it by the components u1 prime of t, u2 prime of t, like this, and then u3 prime of t, like that, close bracket. All right, and now we could just factor these out. Just write it as a vector functions now. So this is going to be the addition of vector functions. This is going to be f prime of t multiplied by u prime of t. That's u regular t, and now plus f of t. And this is going to be u prime of vector function, t, like that. So there it is. Again, we just proved it, and just basic product rule counterpart for vector functions. And just put a check mark right here. And again, this is exactly what we had. And this auto proves formula 2, because that's just based on formula 3. So there it is. And there's formula 3 right here. So f of t, and then u vector function of t, the derivative of this is going to be just the f prime of t times by u of t vector function plus f of t times by the derivative of the vector function u. So yes, epic stuff there. All right, and now that we got that, let's take a look now at exercise 4, and this is proof of formula 5, which is the derivative of a cross product of vector functions. So we're asked here, prove formula 5 of the differentiation rules for vector functions. And basically we have right here, so d over dt, the derivative of the cross product of u of t cross v of t vector functions equals 2. Again, it's always the same component of the product rule, or the same counterpart of it. So now we're going to have u prime of t vector function cross with v of t plus u of t vector function cross with v prime of t. So basically this product rule. Very similar to product rule. All right, and there's two solutions the solutions manual had. One was using the derivative of components, and the other one was the using definition of derivative, which I'll go over after this one. So I'm going to go over right now solution 1, derivative of components, basically using brute force as we've been doing earlier in all of these derivatives. All right, so let u of t vector function equals 2. Again, the usual has u1, u2, and u3 real valued functions as components. And then we have v of t vector function has v1, v2, v3 real valued functions right there as components. So taking the derivative of the components, we obtain, so let's write this down. So d over dt of u of t, like this. So of u of t, u of t cross v of t. And now this equals 2, instead of just memorizing how the product, having the cross product is, we'll write it in determinant format. And first of all, we'll write here d over dt, so the derivative. So we're gonna do this all brute force, and then again write in determinant format so that we can easily it will basically, instead of memorizing, memorize it in determinant format, and we'll follow that easy to memorize setup. So we'll go u1 of t, u2 of t, u3 of t, and now this is the I component, I, j, k, like that. Now we go v1 of t, the bottom part, v2 of t, v3 of t. So this is a cross product in determinate format. And now this equals 2. Again, we're using brute force, d over dt. And now the first component is going to be, well, remember the setup, we cross the first row and the first column, and then we multiply these two, u2 and v3, and then subtract by this one. So we're going to get a u2 of t multiplied by v3 of t minus, now u3 of t, u3 of t, and then multiplied by v2. v2 of t. And now the next component is going to be, well, we erase this part, erase this now, and now we cross out this part. And when we do that, we multiply, but actually the middle one is special, so instead of going the left and bottom right, we go the right and bottom left. So we go there first, so it's going to be u3, u3, like this. Let's fix that up, u3 of t multiplied by v1 of t, and then subtracted by, and now we erase this part, and then now we multiply the other corners. So that's just going to be this one here. It's not sure why it's not erasing. But there it is. Erase and multiply by this. So we get u1 of t and then v3 of t, like that. And I'm just going to keep going further, then we'll just shrink it. And now the next one is going to be, well, cross this out, cross these out. The next one's going to be cross this out, and then multiply by this, subtracted by this, by that. So we're going to get a u1 of t, v2 of t, minus by u2 of t, v1 of t, like that. And this is going to be, this is going to be a vector like that. All right. And then we take the derivative of that. So actually, we don't need to put this extra bracket. So there it is, like that. Alright, here I quickly shrunk that and put it in here, and now I'm probably not going to shrink it, we'll see, because we're going to take now the derivative inside each one. So we basically take the product rule here, product rule here, product rule here, 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 and here. So 6 product rules, so we'll just take the derivative inside. It's going to be equal to now, it's going to be u2 prime of t, like that. So u2 prime of t, and then v3, and then plus, and now the next one's going to be u2 normal, and then v prime of 3. This is t. Okay, so that's the first one. That's this one. So we did one. Now we do the second one. It's going to be now subtracted by u 3 prime of t. And then this is a v2, like that, of t. And then we could just take the negative out, and then basically this is going to be plus anyway, so we're just going to have to a second negative. So this is going to be u3 of t, and then v2 prime of t. So that's the first one, and that's this one. So we did 2. I'll circle each one so we know. So we did this one, we did this one. Now we do the next component is this one here, the y component. That's going to be now this derivative of this one. I used a product rule, so this is going to be u3 of t, v1 of t, plus, and now this is just going to be just again product rule, u3 of t, and then v1 prime of t. So that's this one. Now the next one, subtracted by, we're doing this one here. This is going to be u1 of prime t, v3 of t, and then minus, again, it's going to be minus, this is going to be u1 of t, v3 prime of t. That's this one. And now the next one is going to be u1, this prime, derivative, so v2 of, this is t like that, then using product rule, u1 of t, and then v2 prime of t, minus, and so we did this one. Now we do this one, last one, u2 prime of t, v1 of t, like that, and then we just do minus, whoops, this is going to be minus u2 of t, v1 prime of t, and close bracket there. So we did all that jazz. All right, so let's pull this one. So we did all those, and now the next step is, well, we're gonna factor out. Yeah, we're gonna factor out all the like derivative ones. So this one here, for example, we're gonna factor out as we're gonna write it as 2 different functions or derivatives. I mean vectors. So this right here and this one, we're gonna take those out as separate. So this will equal 2. So put that'll be the component of the first vector. So u2 of u2 of t, v3 of t, and again the reason is because notice the exact same setup here. So we have u2 v3, u2 v3, and this one's u3 v2, u3 v2, but the only difference is the derivative signs are at different locations. So what we'll do is we'll just take the ones with the same derivative signs. This one has derivative here, derivative on the u, no derivative on the v. So we'll put those as together. And then the second vector will have the components u2 of t, v3. So basically has a derivative on the v, not on the u, and then in this one here, derivative on the v, not on the u. So separate those, and so on. So we're going to do this here again, brute force manner. u2 of t, v3 of t minus. This is going to be u3 of t like this. Okay, u3 of t, v2 of t. I'll erase this. And now the next one is going to be, well, this one right here. Yeah, I'll not highlight those ones because those will be separate afterwards. So now this is going to be now comma, and now we just do the same thing here. This one, this right here, and this one. So all the ones with derivatives in the front, and not in the second one. All right, so that's going to be u3 prime of t, v1 of t, minus u1 prime of t, v3 prime of t, like that. All right. So, and now the next setup is going to be, I'll do this and I'll shrink it after. we're going to do this one and this one. So u1 of t and v2 of t. So move this over. This would be prime u1 prime of t and then v2 of t. And now subtracted by this one, u2 of t, v1 of t. All right, so we got this one, and that's going to be one vector. All right, here I just shrunk it to fit one line, so that's that. And then we do a plus. The next setup is basically all the ones without the underlines. Or we could, yeah, we'll do all the ones without underlines. So now we do a u2. And basically it's the exact same thing actually as this, but we just switch up the, yeah, because notice these are the exact same setups. Yeah, as its counterpart right here. So for example, u2 prime, this one's going to be u2 not prime. This one's v3, this is v3 prime. So it's exactly the same setup, but without the primes. This is v3, so we could just do that, and we'll do it rapidly actually. u3 t, v2, and actually, since we have it all, I'll just keep typing it here. Actually, I'll do that. Yeah, I think this is actually more clear actually. So we'll just take this exact setup here. I'm going to copy this and paste it. We're going to put it down here underneath here and move it, shift it over. So we're going to do, again, it's just the same thing, but now we do a plus. And then we take all the primes and then we move it to the other side. So this prime goes here. 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 Yeah, so notice exactly the same setup here. So compare this one here with this one. It says u2 prime v1, u2 v1 prime. So it's exactly the same setup there. And now this is exactly the same thing here as when we got this part here. So u2 v3, u2 v3, u2 v3 is u3 v2, u3 v2. So exactly the same thing. So in other words, we have cross products now, but with this one is with different prime setups. So in other words, we're just going to equal to, I'll just write this for completeness. I'll draw it all out. Yeah, so I'll just write it like this. So I, j, yeah, this is I like that. And yeah, I'll just put it now. The first one's going to be, well, u1 of t, because actually no, these are the derivatives. So this is going to be u prime of t, like that. u2 prime of t. Then u3 prime of t. And now the second one is going to be v1 of t, just normal without the vectors. I mean without the derivatives. v2 of t, v3 of t, and this is the jk. This is k right there. Okay, and now the next one is going to be this one here. So the u's are not the derivative. So we'll have the exact same setup, like this. Make this higher. I'll just do it like this. All right. And this is going to be u1 of t, this is going to be 1 prime of t, like that. u2 of t, u3 of t, and then this is v2 prime of t, and then v3 prime of t, derivative, like that. And then this is going to be like this. And this is I, j, and then k, like that. Alright, here I just quickly shrunk it or just moved it over to this side here. So yeah, we have this basically, and again, it's exactly the same thing. You can cross, you could do the usual setup like this, and cross this out. You're going to get u2 v1 3, u2, this is the second one, u2 v1 3, I'm v prime 3, and then then subtract by this one, it's going to be u3 v2 prime, u3 v2 prime. So again, exactly the same setup. And again, what this means is, again, once we have it in that order, it's pretty straightforward. Now this equals to now, this top part is just going to be the u1, now it's a vector, so the top part is the u, this is the prime of t, cross product with the bottom is just the regular v, vector of t, plus, so I'll just put a plus like this, plus here, and now the next one's going to be derivatives at the bottom. So this is going to be u vector cross with v prime, like that, of t. So there it is. So we solved it. This is the solution 1. And here I just box it better and yeah, just put a check mark there. All right. So yeah, that is the solution. And now let's take a look at the solution again, and now look at solution 2. And then basically using the definition of derivative of vector functions, as opposed to just doing the brute force derivative by components. So we're going to prove this using the definition of derivative. Let's take a look at it right here. So here's solution 2. So alternatively, we can prove formula 5 via the definition of derivatives of vector functions. And before we do that, I just want to note, or basically also note the properties of the cross product from an earlier video, namely property 3 and 4, and also just note, be careful with the order of the cross product here. Here's property 3 from an earlier video, and the link is over here. If you have A cross and then B plus C, well, then you could just multiply the cross products inside A cross B plus A cross C. But note that the order of them, you can't just go multiply A inside here, and you can't just have a B cross A like that. It's not going to be the exact same thing. So this needs to be always in line like that. If it's like this, just don't rearrange how it looks. Just put it inside the cross product for each one. Just add them up. And similarly for A plus B cross C, it's just equal to A cross C and then plus B cross C. So, but you can't just switch them. Yeah, you can't necessarily switch them there. And that's actually because of property 1 right here. Notice that if you switch them, you're gonna have a negative actually. So yes, you have to be careful with that. All right, so let's go further. So let's do the definition. But first of all, I'm gonna go let r of t, the vector function here, equal to, this just equal to the cross product just by themselves. So u of t cross v of t, and then we're going to do the definition of derivative there. All right, so if we have this, then let's go. Then what we'll do is, well, we know that r of t plus h, minus r of t. Again, and then we're going to divide by h after and take a limit and so on. But initially, this is just the the numerator. So this is going to be like this. So now we just do that, expand it out. All right, so this equals to, we'll just plug it inside the u and the v there. So this equals to u of t plus h cross v vector of this is t plus h, and then minus. Now we're going to have to minus the same exact setup there, but with the t. Cross, u of t cross v of t. Like that. So there's a cross product like that. All right, now that we have this, and here what I did was just quickly pause video and shrunk it to fit in here. So so now what the calculus book does actually is it takes the same right-hand side, but then what it does now is it's going to plus. I'm gonna plus right here, and then it's gonna do some quite unique setup here. So it's gonna go plus, and then put this in a bracket like this. No, yeah, actually, we don't need a bracket. So we're gonna just do it like this. So now it's gonna go a plus u of t plus h like this, and then it's gonna cross with a v of t. So instead of t plus h, just as a t there, and then it's gonna subtract it as well, so that we don't change anything. So this is still going to be equal to 0. So plus u of t plus h cross v of t like that. All right. So then this right here just equals to 0. So we're not changing anything there. I'm just going to put a bracket, or I'll just leave it like that. So we just put it like that, or put a bracket, and or actually here I just quickly shrunk it and just pause it. And anyways, I'll just leave it like that. So we don't need to put a bracket, but we just added this separately, and just so that now we could do some tinkering. And yeah, now is where we can apply property 3 and 4. So here's 3 and 4. So if we have this, but now we're going to go with the reverse actually. So if we have a cross b plus a cross c, so we could factor out the a here. So we can factor out the a and then put it outside of the bracket. And then we can just add these c and b, add them up. So that is what we're going to do right now. So now what we're going to do is we're going to take the like term, this one, in this case, this one, and this one, Yeah, and then this one. So this one and this one, we're gonna take those and factor them out, and then we're gonna have these as additions there. But actually, instead of these particular ones, the calculus actually does this one here. So this one and this one, this one and this one, because it has a minus sign. So this has a minus sign. So we want to because we want to eventually cancel some stuff out. So so that's what we have. We're going to take those out. So this is going to equal to u of t plus h, and now this equals to a cross. So we can take this out. This could be our a. This could be our a. And now this is our C, and this is our B, like that. All right, so that's what we all have. Now let's just erase all this, and pretty much got it straightforward. So now it's going to be, and now we'll just a bracket V of T, and again, this is when you have to be careful of the order, so we don't change anything. So it's going to be now plus now V of T, and this is because it's a minus. So we have to minus now. Because we factored out, now it's a minus. So minus. And again, that's why we did the minus side. So we have a minus there. And we'll show this as we keep going. All right. All right, here's quickly shifted it over to this side. And now the next setup is, well, we have these two left over. So we're going to factor out the like term, and that's V of T. Yeah, we're going to factor that out. So that's going to be our new, we'll call this C. This is our C. And then this is going to be our, this is the positive one. We'll move it on to the negative side. Well, this will be our B, and this will be our A. And then that's the property right here. So we'll have A plus B cross C, because this is what we have, A cross C. Instead of a plus, we have a minus. So we have a minus, B plus C. So we're going to separate the C, which is this V of T, and then we're going to get this A minus this B. So instead of plus, we have a minus. All right, let's just all erase all this now. It's pretty straightforward if you just follow along the logic there. Okay, erase this, and erase this, erase the C, and erase the A. Okay, so it's going to be plus, and then we have to keep in mind the order, so we can't just put the V in front. So it's going to be now, this is our A, which is u of t plus h, and then minus this u, which is our b. And then bracket, and then this is going to be now, and then now it's going to be cross product with v, which we factored out using cross product rules. And here, yeah, again, I quickly just moved it over, just shrunk it, fit it inside this one line. So now dividing through by h and taking the limit as h approaches 0, we have, and now we're just going to apply the limit, definition of the limit or derivative of a vector function. So r prime of t is the vector function, the derivative or the tangent vector. This equals to the limit as h approaches 0 of this difference right there. Yeah, this whole thing, again, because that's just r of t plus h minus r of t. So now we're going to plug this whole thing inside, and it's pretty big. So what I'm going to do is, I'm going to just, yeah, actually we'll do this separately. So yeah, we could just take the limit and then also separate it. So I'll just write it all out. Just be probably quicker. R of t plus h, then cross v of t plus h minus v of t, like this. Put a thing like this. Then divide this all out by h, and then this is going to be, yeah, this is, that's one of them there. Alright, here, just fix that up, and now let's go to the next setup. Just shift it over here now, plus, and then put the limit inside on this one here. So limit as h approaches 0 of u, put the bracket like this, u of t plus h minus u of t, and then divide this by, actually a cross product with the other one, cross v of t over h, like that. Alright, so that is what we get. Alright, so now that we have this, well, we could just see what happens here if we just put the h inside here, the first term. We could just get that out of there. We could just take the limit on each separately. So this just equals to, let's plug in this inside. We're going to get a u of t. Yeah, so u of t. So when h goes to 0, we just get a u of t. And now this is going to be a cross with, we could put the limit inside there now, and that's going to be cross with limit as h approaches 0 of v of t plus h. Yeah, because we could just divide the h only on this one here that matters there. Because that looks like the limit. I mean, that looks like the actual definition of derivative for vector function, which it is. And then this is going to be plus. And now same thing with this side here. We're going to get a limit as h approaches 0 of u of t plus h. Okay, this is plus h minus u of t, then all divided by h. And then, and then let's put it here. Now we cross with, and then we just take this limit inside this one. This one doesn't even have a h there. Yeah, so we could just get that out of there and just leave it like that. This is v of t, like that. All right, and here I just shifted this over here so fit it all in one line. And now this one here, this is just the definition of derivative for a vector function. This is just v prime. Yeah, so we have, that's just v prime of t, the vector function. So again, this is just the limit as h approaches 0 of the v of t plus h minus v of t, and then divided by h. And this one is, then this one is the same thing for the u. Yeah, so this is just the definition of the vector function for u now. I'll put it like this. This is u of t prime. So u prime of t, like that, and that's just again a difference u of t plus h minus u of t divided by h. Again, just very similar to the, or just the exact counterpart of the normal functions in their derivative. So then this equals to, well, look what we have. We get u of t cross v of t. Yeah, v prime of t. Yeah, like this, and then plus, now this is u prime of t. And it doesn't matter which order in terms of the addition. And then cross v of t. So there it is. This is exactly the same setup as this, as going back up here. Yeah, going back up here. This is solution 1. We got this one here. It's the same thing. We just have this one in front there. We can just move it over to the other side. It doesn't matter. This is u prime of t. Cross v of t, and this one's u of t cross v prime of t. Again, exact same thing here, and you could shift these around. Addition, you could just, doesn't matter which way it is. Yeah, so there it is, and this is quite fascinating stuff there. Again, just using definition of derivative of vector functions. All right, and here note that I used properties a and d of vector function limits from my earlier video in this derivation. So basically, when I split these apart right here and take the limit, I just used this one here, which is part A. This is properties of vector function limits. This one right here. So when you have a limit of that, you can just split them up like that. And then I also use part D. That's this right here. So when you have a cross product like this, it's the same thing as taking the limit of each one separately. So, and that's pretty much what I did over here. So I took a limit here, this cross product, and I just took a limit inside here and just put the h inside. This one here, this one has no h. I just separate that, and just take a, and then I can set up the definition of vector function limits for these two, and so on. Yeah, so that's quite epic stuff. All right, so now let's take a look at exercise 5, and that's proof of formula 6. Which is the derivative of a function within a vector function, basically a derivative of a function within a vector function, or better worded actually would be a vector function with a function inside, but this is close enough. So basically prove, so we're asked prove formula 6 of the differentiation rules for vector functions. And formula 6, we have this here, d over dt of the vector function u, but then instead of t as a parameter, we have a function as the parameter, or a general function f of t inside. And then when you take the derivative of it, we get, well, basically we take the derivative of u prime of f of t, and then using the chain rule, again, this is a counterpart for vector functions, the same thing, and then just take the derivative of v prime of t. So let's take a look at the solution. So solution, let u of t equals to this vector function with components u1 of t, u2 of t, and u3 of t. And then taking the derivative of the components, we obtain d over dt, and this is going to be u of t, u of f of t, like this, equals 2, and then this is going to be, well, just take that full component, d over dt, and then this is going to be, right here, u1 of f of t, and then u2 of f of t, and we have u3 now, f of t, like that. All right, so we separated that like that, and now we take the derivative inside each one, so this is just going to be equals to, well, d over dt, and then this is going to be of u1 of f of t inside f of t, like this, and then the next one, d over dt, so we do it in each component, u2 of f of t, and then d over dt, u3 of f of t, like this. And again, now we just have a basic chain rule. Now we just have a regular function, it's real valued function, it's not a vector function. This is just a component of it. And then we could just take the derivative and then multiply by the derivative of the inside, which is f prime of t. So this equals to, we're going to get a, this is the chain rule, put it outside, f prime of t, like that, and then u1 prime of f of t, like that. Next one is right here, f prime of t, and then u2 prime of f of t, and then we're going to get a I'm going to put the f again, f prime of t, and then we're going to get a u3 prime of f of t, like this. Oh, we'll put another bracket there, and then triangle bracket. And yeah, here just shifted it over to this side to fit, and now this just equals to, well, it's pretty straightforward. This equals to, well, we have the f prime of t. That's just like a constant now, or it's the, not a constant, but a common factor. Would you take it out of this whole vector? So we just get a f prime of t, and then this is going to be u prime of t, f of t. Like that, just for completeness, write the whole thing out. This is going to be u2 f of t, like that, and then u3 prime of t. And lastly, yeah, this is just a vector u prime of t. So this equals to f prime of t u prime of t vector function. There it is. And that is it. Yeah, so that is exactly what we had here. So there's a chain rule, and again, as a counterpart of it with vector functions. So absolutely fascinating stuff there. And yeah, that is all for today. Again, quite an extensive video right here as per usual. And yeah, that's all for today. Hopefully you enjoyed. And again, all these notes and the links will be in the description below. And the notes will be on the Hive blockchain in article format, as well as in PDF format where you can download as well as that. Yeah, so quite fascinating stuff there. And I'm just going to keep scrolling all the way up. So we got quite a bit of scrolling to do. And then I'll be uploading the sections playlist as well. Basically, I'll be uploading these clips in short format as well. And just, yeah, basically I'll upload the full video, multi-hour video, and then short clips throughout this coming days. Anyways, that is all for today. Thanks for watching, and stay tuned for another Math Easy solution.